Hello, differential equation students. So in this video, we'll talk about how do we solve first order linear differential equations. So if you recollect, we in this couple of videos, we talked about how do we solve first order differential equations. So before we solve, we looked at without solving, what are the things that without looking at the solution, what are the things that we can do. So we talked about the direction fields, and then we also talked about how do we work with an autonomous differential equation, using phase plane and phase portraits, and also we can talk about the stability of all these things. So again, these are qualitative behavior. What are the things that we can do? We don't know how to find the solution yet, but we can look at some qualitative behavior of the differential equation. In the section in the variable separable method, in the previous video, we looked at how do we solve variable separable differential equations. And we have a wonderful method that can be helpful as long as the function is the y prime is equal to f of x y, where this f of x comma y has this nice structure in there. Again, we looked at how do we solve that. So in this section of linear equations, let's take a look at how do we solve first order linear differential equations. So what is the first order linear differential equation? A first order linear differential equation is something that looks like this. What do I mean by that? So you have a dy over dx multiplied by a function of x, and you have a y multiplied by a function of x, and then you have a gx, right? This is called the first order linear differential equations. If you want to write this in a simple term, in simple way, you can say this is a sub a1 of x times y prime plus a sub 0 of x times y is equal to g of x. If this g of x happens to be 0, we call that as a homogeneous linear differential equation. Otherwise, it is called non-homogeneous. What do I mean by otherwise? By which I mean that if g of x is not equal to 0. We'll see some examples in a moment, but this is how we define a first order linear differential equations. Now, when we try to solve the first order differential equation, the method that we're going to use requires us to simplify this in the standard form. So what do I mean by the standard form? In the standard form, we basically we want the coefficient of the dy over dx, or the y prime, to be 1. So we want this to be just by itself, right? The coefficient to be 1. So then if that is the case, then whatever you get is what we call the standard form, right? So this is what we call the standard form, or you might be able to rewrite it. So I'll show you how these are going to be more useful and important. The most important thing is that, so once you write in the standard form, when the coefficient for this is 1, whatever is the coefficient of the y is what we call p of x, and whatever is on the other side of the equation is what we call the standalone function of x, is what we call the q of x. So just in case, how do we do that? So when someone gives you this equation, you're going to divide the entire equation by a1 of x. So there, you are going to have a dy over dx plus a sub 0 over a1, and y is equal to g over a1. So that's what you're going to have, something like that, right? All right, now let's take a look at these, some examples of the linear equations. So here's another nice example of linear equations. Let's try to identify our p's and q's. So in this one, if you take a look at the p, so here's my p, and here's my q. So therefore here, p of x is equal to 1 over x, and q of x is equal to e to the negative x. And by the way, this is a non-homogeneous first order linear differential equation. The homogeneous version, I'm going to call HOM version, homogeneous version for this would be y prime plus 1 over x times y is equal to 0. So if you take a look at the second example, again, this is already nicely in the normal form. So here, this is going to be my p of x, and this is going to be my q of x. So therefore, I can say p of x is equal to x squared plus 1 over 2, and q of x equals x over 2. And again, the homogeneous version of this would be y prime plus x squared plus 1 over 2 times y is equal to 0. Now let's take a look at the number 3. Number 3, I don't have the coefficient is the coefficient of the y is not 1, so it's something x. So I'm going to divide to write this, to identify the p and q, to write this in the standard form. What I am going to do, I'm going to divide by x. So if I divide by x, ladies and gentlemen, I am going to get y prime minus 4 over x times y is equal to x to the 6e to the x over x. And again, I can cancel the x over here. So if you do that, then the standard form is going to be y prime minus 4 over xy is equal to x to the 5e to the x. And so therefore, for this particular one, the p of x would be negative 4 over x, and the q of x would be x to the 5e to the x. Again, if you're not paying attention to this, if you don't write this in the standard form, you may mistakenly identify your p of x as negative 4 and the q of x is x to the 6e to the x, which will result in the wrong answer. So keep that in mind. Let's take a look at the number 4. If you take a look at the number 4, this already, the coefficient is already 1, so that's good, and that's very good. And so therefore, the p of x in this case would be a very nice one, which is negative 3, and the q of x would be as simple as 6. So although it looks like a constant, yes, that's a function of x. These are constant functions, and that's okay as well. So here, the homogeneous version is going to be as simple as y prime minus 3y is equal to 0, and that's how we identify the p's and q's of the linear first order linear equations. So now, how do we solve that? To do that, I want to quickly talk about what we call integrating factor. So what is this integrating factor business? So this integrating factor is basically so we usually we have this differential equation. So we have this differential equation of y prime plus p of x times y is equal to q of x, right? We have this particular differential equation. Now the question here is there something that I can multiply? Is there something that I can multiply so that I can rewrite this entire thing as a single entity, and hopefully derivative of something, So basically, is there something that I can multiply with this that will make this one integrable? So that's what we call integrating factor. The one that makes the left-hand side to be integrable is what we call the integrating factor. The factor that makes this is integrable, right? So how do we do that? So to do that, let's not worry about the non-homogeneous one. Let's take a look at the very simple homogeneous version of it. The homogeneous version of it, as you see, for this one would be y prime plus p of x times y is equal to 0, right? So again, the question is there something that I can do or multiply with this that will make it integrable? Yes, there is something that we can do, and that is, as a matter of fact, is e to the integral of the function p of x dx. I know it's a lot of things in there. Again, we are also using here, in this particular one, we are using the indefinite integral. We can also use a definite integral. Probably we'll talk about it later, but right now let's just go with the indefinite integral, one that does not have upper limit or the lower limits. So when I multiply this one with this differential equation, let's see what happens, right? Let's see what happens. Now, what I have here is I have e to the integral of p of x dx times y prime plus p of x times e to the integral of p of x dx times y is equal to 0, right? Now, let's skip it for a while, but I want you to take a step back. I'm kind of going backwards. I want you to find the derivative of this one for me. If I have this function y times e to the integral of p of x dx, again, use your calculus 1, what would be the derivative of this particular term? Right? What would be the derivative of this particular term? You can use the integration. You can use the chain rule, and you can use the product rule, and then you're also going to use the first fundamental theorem of calculus to do that. So, take a few moments, don't look at the video now. Take a few moments and see if you can do it. If you cannot do it, come back and watch the video, but take a moment for now and then see how do you do it. So now let me do it. If I try to do this, if I use the product rule, I'm going to find the derivative of the first one, which is going to, I have two equations in here. I have two functions in here, y and e to the p of x dx. So if I try to find the derivative of the very first one, I'm going to have a y prime. I'm going to keep the second one as is, as per the product rule. So I have e to the integral of p of x dx, plus I'm going to keep the first one as is. I'm going to keep the first one as is, and I'm going to find the derivative of the second one. When I do that by the fundamental theorem of calculus, this would be simply e to the integral of p of x dx, right, by the chain rule times the derivative of this particular one, and the derivative of that particular one is going to be, as you know, that is going to be by the fundamental theorem of calculus, that is going to be p of x. That's it, right? And then that's all I have. So that is the derivative. And do you see anything? Do you see anything that resembles, right? As a matter of fact, if you take a look, right, this is exactly this one right here. This one right here is exactly same as this one. Although terms are rearranged, right? This one is exactly same as that one. So now, I achieved what I wanted to achieve. Now, if I multiply e to the p of x dx with this particular equation, the right-hand side of the equation, right? What I get is this left-hand side, this whole left-hand side becomes a single term, right? The whole left-hand side becomes a single term, and that means it'll make my life much, much easy to solve. So let's see, how do we solve that? So now what I'm going to do to solve that, what I'm going to do is what I'm going to do. So I have this equation right here, right? I have this equation right here. Now what I'm going to do is I am going to, let me just shrink these things to make my life easy. All right. I'm going to say IF, by which I mean integrating factor. So now what I'm going to do, I'm going to multiply this integrating factor with this one, right? So when I do that, I have e, if I'm going to multiply this, e to the integral of p of x dx multiplied by y prime plus p of x times y, and then that is equal to e to the integral of p of x dx times 0, right? The left-hand side, thanks to the derivation that I did earlier here, right? That if I distribute it, I'm going to have this one. If I distribute it, I'm going to have this one, right? I'm going to have this one, so which is same as this, so therefore which is same as that, right? And I multiply, that's what I have. So when I multiply e to the p of x with the first equation, I'm going to have this, which is exactly same as this one. So I'm going to copy paste it in here. So you see that now the left-hand side turns out to be y times e to the integral of p of x dx, the derivative of that. And the right-hand side is anyway, it's a 0 times anything is 0, so it's going to be 0. Now, since I have the derivative, I can integrate both sides. I'm going to do what I call IBS. I'm going to integrate both sides. I'm going to integrate both sides. When I do that, what's going to happen is that integral of y e to the integral of p of x dx, right? And then the dx here, again, I'm using, indefinite integral, so no limits in here, no limits in here. You can do that too later, but I'm not gonna, let's not worry about it for time being. We'll talk about it later. Is going to be equal to this integral of 0 dx, right? And then what happens when I do that? When I do that, what happens is that the left hand side, right? The left hand side, by the way, here's the derivative. The left hand side, because of the again fundamental theorem of calculus, the integral is the antiderivative. Antiderivative of the derivative is the same. So therefore, the left hand side is going to be simply y times e to the integral of p of x dx, and the right hand side is going to be c. Again, our goal is to find the solution y, right? So therefore, our y is going to be c times, where c is an arbitrary constant, c times e to the integral of p of x dx, and that's your solution there. So you're going to say where c is an arbitrary constant, right? And that is how we find, that is the method, and that's why we call this is that's why we call this is a integrating factor. And that's because, and that's how we found the solution to the first order linear differential equations, which is homogeneous. So let me, so here's the basic theory of how we get to this. Now let me give you the steps in which we can solve this, right? The steps that we can follow to solve this. At the end of the day, if you take a close look at the solution, ladies and gentlemen, here is a solution. As far as the solution is concerned, when you have a differential equation, which is y prime plus p of x times y equal to 0, right? As far as the solution is concerned, that only involves e to the integral of p of x dx. So you identify your p, you integrate it, right? And then you raise it to the power e, multiply by a constant that's going to give you a solution. So what are the methods in solving this? So if I have to come up with a method, the method is going to look like this. If you want to go with a process or a procedure. Step number one, make sure to write the differential equations in the standard form. Write the differential equation in the standard form. That's a step number one. Step number two, identify your p of x, right? Step number three, and find the integrating factor. Find the integrating factor, which is you first integrate p of x with respect to x, raise it to the power e. Then the solution is as simple as this. I think I may have made a mistake in here. There should be a negative, by the way, right? So then you write it, y times e to the integral of p of x dx equal to c, and next step is solve for y, right? Solve for y. I'm going to say solve for y, so you can solve it. I'm going to say solve for y, and that is a very similar process that we're going to use for the non-homogeneous as well. Again, remember, we are talking about the homogeneous differential equation, so this is going to be y prime plus p of x y is equal to 0, right? This is for solving homogeneous linear first order differential equations, right? Or first order linear differential equations, whatever you want to call it. First order linear differential equations. So let's see, let's work out this process for all these steps for this particular example. So step number one, let's take a look at this example. Right? So step number one, as I said, is going to make sure it's in the standard form. Luckily, it's already in the standard form. So we don't have to worry about it, right? Hakuna matata, right? It means no worries. Step number two is to find the p of x. In this case, the p of x is, if you really pay close attention to it, this is your p of x. That's going to be your p of x. So which is, negative 1 over x. The next step is to find the integrating factor. Further, what I'm going to integrate. So next step is to find the integrating factor. I'm going to integrate, negative 1 over x dx. You're all experts in integration. If you integrate it, you would agree with me this is going to be negative ln of x. All right, don't worry about the plus c and all. We'll worry about the plus c at the end. Don't worry about it. Integrating factor, do not worry about adding a plus c, right? Don't worry about adding a plus c. It will be taken care anyway, don't worry. So that's why, this c will capture that. All right, and so therefore the integrating factor is going to be, e to the negative ln of x, right? The integrating factor is going to be e to the negative ln of x, which is, if you simplify, by the way, it's going to be 1 over x. And so therefore the next step number 4, I'm going to write y multiplied by the integrating factor, which is 1 over x, is equal to c. Now the next step is to solve for the y. If I try to solve for the y, now it's going to tell me y is equal to cx, where c is I'm going to say AC, by which I mean arbitrary constant. And that's how you solve homogeneous first order linear differential equations using integrating factor. So that's what I mean by integrating factor in here. So that's a very, very important. It plays a vital role in solving this first order linear differential equations. Now let's take a look at how do we solve nonlinear differential equations. Before I go any further, I'll give you another another example for you to work it out, right? So maybe I'll ask a quiz on this, right? So, as an example, why don't you try this as an exercise? I'm going to say as an exercise, try this, y prime plus x squared plus 1 over 2 times y is equal to 0, right? Try this and try to follow all these steps. Now let's take a look at how do we solve non-homogeneous linear differential equations. The idea, the steps are very similar, but we're going to add some more things to it, right? We're going to add some more things to it. So let me show you what I am going to do, right? So I'm going to show you this way so that you can, I'm going to copy this so that you kind of follow me. Exactly what are the changes. I'm going to copy. I have the luxury of copying it. All right, so let me copy the differential equation 2. Now, by the way, I should add here just in case, we are looking at y prime plus p of x equal to p of x times y equal to 0. Now let me copy this one. So this is what we're trying to solve, right? This is what we're trying to solve. Now what I have here is, I have now, which means I'm going to take this off, and I'm going to have q of x in there, right? So let me do that. So this is z is going to go away. Now I will write this in a different color so you know the difference, right? Now I have a q of x. So therefore this is also going to be q of x, and this is no longer a 0, right? So keep that in mind. This is no longer a 0. Now what I have here is I have this whole thing here again, right? Now again, by the same token, I no longer have the 0 dx, but instead what I have is, I am going to have, this one right here. Make it a bigger one. Then I'm going to integrate this with respect to x, right? So these are the changes as far as these things are concerned. Now let's take a look at how do we work with this further. So that's what I have, right? I think, what did I do here? Something had, yeah, a few things are messed up. It's okay, I'll fix it. So that's what I have. And let's see what happens. All right. Now again, if you're going to integrate both sides after this step, right? After this step, we're going to integrate both sides. When I integrate both sides, what I'm going to have is my left-hand side is going to be y times e to the integral of p of x dx. That does not change anything, right? But the right-hand side is going to have, huge this integral of e to the integral of, p of x dx times q of x dx, right? I have this, huge integral, but again, I have to solve it. So then next step, what do you do? Then solve for y. So you do the integration, right? Do the integration and then solve for y. Then you're going to have, c here and there and so on. You're going to have that c, and then you're going to work with that c, and you're going to solve all that. Then you're going to have the next step, you're going to solve for y, right? Next step, you're going to solve for y. So that is the same idea that we had before. Nothing else changed except that rather than having a 0, 0, 0, 0, 0, 0 here, now we have a long expression, but that's again, integration, kind of like, two integrations, integration inside the integration. You have integration raised to the power e, and then, integrate again, multiply that with the q, and then integrate again, right? So you have more integrations, but anyway, you know how to solve them, so you can work with them. So that is the theoretical aspects in solving solving non-homogeneous first order linear differential equations. Now as a step, what we are going to do? So we're going to follow the same step. So I'm going to some extent, and then I'm going to change a few things in here. So let me copy this for you. So same steps are going to work, except a few things are going to be different. All right. Okay, let me just move this one over here. We don't need this anyway because we already have it on the bottom. So what we are going to have is solving non-homogeneous, right? So here, rather than having a z, you're going to have this, this integral right here. You're going to have this integral right there. So you have integral e to the integral of p of x dx multiplied with, q of x dx. And then whatever you get, then you're going to solve for y. That's all. There is no other change at all, right? The exact same thing that we had. But in as far as the process is concerned, it might look simple. But then when you try to work out execute the process, you're going to see there's going to be a little bit more computation involved. So let's apply this method to solve this particular problem. So step number one, y prime minus 1 over x times y is equal to 3x. Again, I chose this problem because this is easier for you to follow. So we know that we already solved this one, right? So only thing that is new in this one is just 3x, but I chose this one so that it's easier for you to follow. So the step one, it is already in the standard form. So as I said, Hakuna Matata, it means no worries, right? It's already in the standard form, no need to worry about it. All right, so I have y prime minus 1 over x y is equal to 3x. The step two is to identify our p of x, which we already did it, but just in case, our p of x is negative 1 over x. Here we also have to identify the q of x. And the q of x is here is equal to 3. Q of x in this case is 3. The next step, again, we're going to find the integrating factor. To do the integrating factor, I'm going to integrate the p of x, which is negative 1 over x, dx, which is going to be, negative ln of x. And therefore, the integrating factor is going to be e to the negative ln of x. Again, if you use the exponential properties, this is same as saying e to the ln of x to the negative 1, which is e to the ln of 1 over x, which is, again, exponential function, logarithmic functions are inverses of each other. You know this from your college algebra. So that is going to give me 1 over x. The next step is a little bit more involved, but we can do it, which is, now I'm going to plug it back into this particular form right here, and then I'm going to work through with that, right? All right, so let me do that. So I have y times the integrating factor, which is 1 over x, and my right-hand side, right? My right-hand side is going to be a little bit involved. So this is going to be integral of, we already know the integrating factor, which is 1 over x, times q of x, which is 3 times x dx. And again, I chose the one that are easier for us to do. My goal is to not to do the very complex integration, but you should know how to do the complex integration. Again, you do have problems doing this complex integration. The good news for me is x and x gets canceled, and what I have is I have simply the integral of 3 dx, which is equal to 3x plus c, which is equal to 3x plus c. So what I have here is I have y over x equals 3x plus c. And again, as I said earlier, the next step is to solve. Next step is to solve for y. This is very simple. If I solve this for y, I'm going to have y is equal to 3x squared plus cx, where c is an arbitrary constant. And again, if I give you the value, some sort of an initial value, then you should be able to figure out that c. What do I mean by that? So for example, suppose if I say, well, my y of 0 is equal to 1, right? Then we should be able to figure out the c. How do I do that? I'm going to plug in 0 into my y. We know that that is equal to 1 from the initial condition, which is equal to 3 times 1 squared plus c times 1. That I have here is 3 plus c is equal to 1. So this tells me c is equal to minus 2. And so therefore, the differential equation, the solution to this initial value problem, the solution to the initial value problem, which is y prime minus 1 over x, y is equal to 3x, where with y of 0 is equal to 1, right? For this, the solution is y of x equals 3x squared minus 2x, right? Because now we figure out the c, and that's how we find the solution to the initial value problem, and that's how we do these kind of problems. That's pretty much is how do we solve first order linear differential equations, both homogeneous and then non-homogeneous part.